Alright, so I'm going to wrap up our probability portion of this project. So I'm going to talk about mutually exclusive and independent events specifically, along with the binomial probability theorem, which has to do with independent events. So first off, we'll talk about mutually exclusive events. So these are just events that can't occur together at all. So it means there's no intersection between the two events. So getting like a head and a tail, you obviously can't get both at the same time. Or having like a diamond and a heart face card, you can't end up with a diamond and a heart that's on the same card. So those would be considered mutually exclusive. And our equation that we use is P with A and B, where probability of event A, you add it to the probability of event B. And the other thing is if there was an intersection, you then have to subtract it. So that's what we saw with Lauren's presentation, or you have that extra step where you subtract the probability of A and B occurring together. So that would be like a diamond and a 7, because a 7 can be with 4 other suits. So let's move on to our first example. So I'm going to go back to the coins. So if you flip 2 coins at once, what is the probability of getting them tails or 2 heads? So there's 2 methods you can go about this. You can make a table or you can make a tree diagram. I'll show the tree diagram after this, because that's really only helpful if you flip it more than 2 times. Then it's helpful to see the tree diagram. But when you only do it 2 times, then you can see it with the chart. So the first step is to make the chart, like we saw. So you have your first coin, second coin. So obviously you can get a tail or a head, or you can get a tail or a head on both coins. So when you flip it once, you have the probability of getting 2 tails, 2 heads, a tail and head, or a tail and head. All right. So then we move on to solve this. So we have to bring up the equation of mutually exclusive events, where the probability of A plus the probability of B. For in our case, our probability of A is going to be 2 tails, and our probability of B is going to be 2 heads. So we find that by going back to our chart. So we see that 2 tails is only 1 out of the 4 chances, and we see that 2 heads is also only 1 of the 4 chances over here in the corner. So we add those 2 together, and you end up with 2/4 or 1/2 to simplify it. So anybody have any questions about that? Makes sense? Cool. So we're going to move on to see the tree diagram. So this, like I was saying, this gives you the same exact outcome. So you put your head and your tail, and then when you flip the coin, you obviously are going to get another head, tail, head, or a tail. So these are the same things where you have 2 heads, head and tail, 2 tails. So if you're going to flip it again, then you would put like head, tail, and so forth. So it's more, as you do more flips, it's important that you follow the tree diagram post the chart, because the chart would be difficult to go around. So let's move on to the next example. So we're going to go to the face card. So if you choose a card from a deck of 52, what's the probability of getting a diamond or a heart? So once again, we revisit our formula, which is the probability of A plus the probability of event B. And then we see that our probability of A is going to be the diamonds, which out of a deck of 52, there's going to be 13 cards that are diamonds, because you have 3 face cards, you have the ace, and then you have 9 number cards. And it's going to be the same thing for the hearts, which is also 13 out of 52. So we add the 2, and you get 26 over 52, which is also simplified to a half. So when you pick a card out of a deck of 52, you have a 50% chance of getting a diamond or a heart on that when you pick a card. So now we're going to move on to independent events. So this is the other section. So these are events where one occurring doesn't affect the other event occurring. So in order to solve this, we use the formula of the probability of A times the probability of B, which is different from mutually exclusive events where you add them. With independent events, you multiply the 2 events together. So once again, we're going to look at an example. So this is easy to see with dice, when you roll dice, 2 at a time specifically. So what is the probability of rolling 2 dice and getting a 9 2 times in a row? So for the easiest thing to do for this is also to make a chart. So you end up making a chart like this, where you have you have 1 die, you have another die. So you put, since there's 6 numbers on the die, you put 1 through 6, 1 through 6. So this accounts for every time you roll the dice, different number of combinations that you'll get. So if you see, like if you roll a 1 and a 1, you get 2. If you roll a 4 and a 4, you end up getting an 8, which is blocked out by this. But for our case, for the question, we're just worried about the 9s. So if you look at the 9s, when you roll a 6 and a 3, obviously get 9, because 6 plus 3 is 9, and 4 and 5, and so on. So when you roll 2 die, you have I'll go through it. So the probability of the independent events, we're going to also go back to the formula. Probability of A times probability of B, like we saw before. This is what I was about to talk about. So as you can see, there's 4 times that you can get a 9 when you roll 2 die, and there's 36 combinations if you add all these up, or 6 times 6. There's 36 different ways, or 36 different numbers combinations that you can get. So since out of the 36, there's 4 9s, there's a chance of getting 4 9s. You 4 over 36, which simplifies to 1/9. And then since our question is asking for it 2 times in a row, our probability of A is actually going to give you the probability of 9, and our probability of B is also going to be the probability of getting a 9, because it says 2 times in a row. So that's like doing the probability times each other. So you end up doing 1 over 9 times 1 over 9, which gives you 1 out of 81. So when you roll 2 die, the probability of getting a 9 2 times in a row is 1 out of 81. And notice the change in notation as well. We're no longer using the uppercase U, use the lowercase u for independent events. So just to make a difference between mutually exclusive and independent events. Everybody understand that?
Mm-hmm.
All right. So now we're going to go to the second example. So it's the same exact scenario. You're rolling 2 die, but this time we're asking for a 9 and a 3. So you're going to do the same exact process. You're going to look at the chart, but this time you're going to account just for the 9 once because it's not asking for it twice, and you're also going to count for the 3. So we're going to go back to the formula again, where you have the probability of event A times probability of event B. But in this case, the probability of A is going to be either a 9 or a 3, and then there's going to be the other one for probability of B. So I made my probability of A as 9, and my probability of B as 3. So you have a 4 out of 36 chance of getting a 9 like we saw in the last problem, which is 1 over 9. And then you have a 2 out of 36 because there's 2 3s right there. You either roll a 2 and a 1 or 2 and a 1 with the other die. So it gives you 1 out of 18. And then you multiply the 2 together again, and you get 1 out of 162. Or 1 over 162 probability. So when you roll the 2 die, that you'll end up with a 3 or a 9. So now we're going to move into the probability theorem, but before we do this, there's 2 little lessons that we have to go over so you can fully understand the concept. So combinations, like we saw before, so this is choosing any number out of items R, which R represents the number of items that you're choosing, out of N, which is the total number that you're choosing from, when the order doesn't matter. So this is represented by N choose R, so the R would be what you're choosing, N is the total number, which equals this equation. This is like a factorial symbol, which means that it's all the numbers multiplied together. So if it said like 3 factorial, it would be like 1 times 2 times 3, or like 5 would be 1 times 2 times 3 times 4 times 5. So the good thing about this equation is that one of the factorials always ends up canceling out like one of the higher factorials, which we'll see in the problem. So you don't end up having to do a whole lot of math here. Although it looks like a lot, it really simplifies itself out. And then we're also going to review the complement principle. So this is when the sample has all the possible outcomes when you're given a range. You know the probability must be 100, so you take the other side of the 100 from what you're given. So this is represented by the probability of the complement A, which is equal to the 1 minus P over A, or P of A, or you could also do 100 minus the percentage that you're given. So that's just a quick review. Now we're going to go independent events repeat each other, that there must be 2 possible outcomes. So when you look at a problem, if there's 2 possible outcomes, you're going to mostly relate to this theorem. So I'm going to run through the example real quick. But before, you just have to know the formula. So it's represented by P plus Q to the 9, where we see P is the event that you're going to try and find, and then Q is the complement of that event. So say this was like 80, this would end up being 20. Then N is the number of times that the event is repeated. So if we look at an example, we see that in 2015, 75% of the population watched 3 hours or more of football. In a survey, there were 10 people who were chosen. And what is the probability that 7 people watched 3 hours or more of football? So we go back to our equation. So we just kind of put that next to it so we can understand what we're looking at here. And we start to interpret the problem. So our P plus Q is going to end up being 0.75 plus 0.25 raised to the 10. Since P, that 7 people watched 3 hours or more of football is 0.75 because our percentage that people that did watch football is 75%. So then you take the complement, so you do 1 minus 0.75 or 100 minus 75%, you get 0.25 or 25%. And then since there were 10 people that were chosen, your number of times that the event is repeated is 10. So then you go to solve, so like I was saying, it's going to be 0.75 plus 0.25 raised to the 10. And then you're going to, since it's a binomial probability theorem, and they're asking you for a certain amount, you have to take into account the combination of selecting all the one person and all the different ways that you can select that person. So that's when you have to bring in the combination concept. So since it's asking for 7 people, you do 10 choose 7. And then since you're trying to find some people that did watch football, you're going to raise that 75% that the one person that did to the 7th, and the 25% to the 3 to account for the 10 people that they're selecting from. And then the combination ends up being, since the N was 10 and the R is 7, So it's 10 minus 7, the factorial of that, times 7, and 10 over all that. And you still account for the 0.75 and 0.25. So if we go and solve that real quick, you see here how it goes to 10 times 9 times 8 times 7 factorial. This is already a 7 factorial, and this is a 3. So that ends up canceling out. So you end up with just 10 times 9 times 8, which is 720 over 3 factorial, which ends up being 6, which is 1 times 2 times 3. So we solve all that out, we end up with 120. 0.7 to the 7th is this long decimal, and 0.25 to the 3rd is this long decimal. So that gives you about 0.25, which gives you 25%. So that means that out of all the ways that you can select people, the probability of selecting one person, or the possibility that you select one person out of the 7, that watch football is 25% out of all the ways of selecting out of 10 people. So I'll take that back, I'm sorry. When you select out of 10 people, there's a probability of 25% that 7 of them that one of the 7 is going to be watching football. So everybody kind of understand that? Mm-hmm. Yeah, makes sense? Okay. So just going on to conclude, so mutually exclusive events are events that don't occur together. Independent are ones that one doesn't affect the other one. Binomial probability theorem is when all the events, when multiple independent events occur together, but there's only 2 possible outcomes. So I know we're kind of pushing the gap here, but is there any questions? All right.